Hello everyone. Hello everyone. Welcome to the learning field. Welcome to the channel. So this is the section. This is the question discussion session of what? Of GATE 2016 and GATE 2015. Okay, because there are two questions only in GATE 2016 and one questions only in 2015 from the GATE LPP section. Okay, because that time statistics is also included in the syllabus. That's why the weightage of the LPP is very low for the this years of questions of GATE. But now the questions since statistics is an different paper in the GATE exam, therefore from this 2020 or 2020 after 2019 the weightage of LPP is very high in the GATE mathematics exam. Okay, so there are only 3 questions from GATE 2016, 2 questions and 1 question from GATE 2015. Okay, so let's start to solve the questions and the questions are very easy problem also. Okay, so let's start, and before starting I am requesting to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and subscribe the channel. Okay, so let's start with question. This is a question 51, question number 51, NAT type question, and this is from GATE 2015. Okay, GATE 2015 paper. The question says that consider the linear programming problem, maximize 3x1 plus 9y 3x plus 9y subject to 2y minus x less equal to 2, 3y minus x greater equal to 0, and 2y plus 3 2x plus 3y is less equal to 10. Okay, so these three are the constants. So this is a very easy problem. We first draw the graph of the LPP. Okay, because this is a simple maximization problem. Okay, so the first equation is corresponding to the first constant is 2y minus x, this is equal to 2, and this red equation is the equation what? 2y minus x, this is equal to 2, and now the second equation is 3y minus x, this is equal to 0. That is, this is the equation 3y minus x, this is equal to 0, and the number third equation is what? 2x plus 3y equal to 10. So this is the equation 2x plus 3y, this is equal to 10. So now see, if we put 0 0 in the first constant, this put 0 0 0 less equal to 2, which is satisfied. Therefore what? 2y minus x, this is inside this region. Okay, so this is the region is towards the origin. Okay, if we put 0 0 in the second constant, this is an constant which passes, equation which passes through 0, therefore we put another point. Suppose we put 1 1. If we put 1 1, then what? In the given equation, then the region is 1 1 means 3 minus 1, 3 minus 1 is equal to 2, which is greater than 0, satisfies. That is the region towards 1 1, and 1 1 point is at this. Okay, so the region is in this side, and one more thing, one more equation is 2y plus 3x, 2x plus 3y, this is equal to 10. Okay, so if we put 0 0, then this satisfies the equation 0 less equal to 10. Therefore the region is towards the origin. Which is the region? Towards the origin. So this is the region towards the origin. Okay, so the region is this one. Okay, so this is the our region. Okay, so this is the our region. Now we find the corner point, that is the extreme point, this one, and this one. Okay, so the corner point of this equation, so this is 2x intersection of 2x plus 3y, this is equal to 10, and what? X 3y minus x, this is equal to 0. So if we put x equal to 3y to here, so we get 5, x equal to 3y, so 4x is equal to 10. This gives x equal to, just a second, I think this is wrong, just a second. Yes, this is the corner point. What? Just a second. And this is clearly, you can see that this is the point 2 2. Okay, so this is the point 2 2. You can also find by solving these two solution, this one and this. Okay, and this is the I think point what, just a minute, this is the point 10 by 3, I think 10 by 3 and 10 by 9. Okay, just skip the calculations. Okay, and this is the 0.01 and this is the 0.00. Okay, so you can calculate by using your own calculation. Okay, so the 0.22, now we find the objective value of the objective function of these points. Okay, so the objective functions in z equal to what, 3x plus 9y. Now at 0 0, at 0 0, this is equal to 0, at then at what, at 0 1, this z equal to what, 9, at 0 1, 10 by 3 and 10 by 9, the value is 3 into 10 by 3 plus 9 into 10 by 9, which is equal to 10 plus 10, this is equal to 20, and at this 2 2, the 0.22, the value is z equal to what, z equal to 3 into 2 plus 9 into 2, so this is equal to 6 plus 18, this is equal to 24, and we have to maximize the z, so therefore the maximum value of z is 24 here. Okay, therefore the maximum value of the objective function is 24. Okay, so this is the solution of the problem of GATE 2015. Okay, now we go to the next problem. This is these two problems comes in GATE 2017. Okay, these two problems are from 2017, and question number 44 and question number 45. So question number 44 says that minimize w equal to x plus 2y subject to 2x plus y greater equal to 3, x plus 2y greater equal to 2. Okay, so these two are minimization problem with greater equal to inequalities. We can solve by using this by taking this problem, and now I take the dual of this problem for this solution, because we know that the objective value of the primal problem and objective value of the dual problem are same. Okay, so if we take the dual of this problem, because I think dual should be more perfect for this problem. Okay, so dual, suppose the dual variable is u and v. Okay, therefore the maximize, suppose z equal to what, maximize z equal to 3u plus 2v, and subject to what, subject to 2u plus v, 2u plus v less equal to 1, and the another one is u plus v which is less equal to 2, I think. Okay, yes, now we should draw the graph. Okay, so if we draw the graph, then this gives a 1 by 2 and 1. Okay, so this is suppose 1 by 2 comma 0 point, and this is suppose 0 comma 1 point. Okay, because from this first equation we get 2 points, but from it intersect form. Okay, so this is the line, and another line is 2, suppose this is 1 and this is 2. Okay, 2 0, this is u. Okay, this is v, 2 0 and 0 2. Okay, suppose this is 0 2, so this is the line. Okay, 2 0 and 0 2. Okay, now if we put 0 0, then this satisfies, these both are satisfied, therefore this side is the region for both the lines. Okay, therefore the common region is what, the common region is this one. Okay, so this region is the common region. Just a second, the common region is this one. Okay, so the common region is the extreme points are what, 0 0, half 0 and 0 1. Okay, now we find the value of the dual. So this is 3u plus 2v, 3u plus 2v. At 0 0, the value of z, this is equal to 0. At half 0, the value of z equal to 3 by 2, and at 0 1, the value of z is equal to what, is equal to 2. Okay, so z equal to 2, and we have to maximize in case of dual problem, since this is minimization problem. Therefore the maximum value of z equal to 2 for the dual of the given primal problem. Therefore the objective value of the minimization problem, that is the primal problem, is also equal to 2. Therefore 2 is the correct answer of the problem. So this is, I think, easy if you convert the problem to its dual. Okay, Now we're going to the next question. We're going to the next question. The next question, question number 45. Question number 45 says that maximize w equal to 11x minus z subject to this one. Okay, so see, there is a note. You can see that there is three variables. Okay, three variables. So we can solve it by, we cannot solve it by graphical method, simple graphical method, and we have to solve it by use of simplex method, by the use of simplex method. Okay, but if we can reduce the number of variables, from 3 to 2, okay, then we can solve it by graphical method. That's why we solve, or we convert the problem to the dual. Okay, if we convert the dual, this primal problem to the dual, then the number of constant is equal to the number of variable. In case of primal and dual, you can you know it. Okay, so if we convert that its dual, then the dual problem is what? The dual problem is minimize z equal to, suppose the dual variable are u and v. Okay, suppose the variable are dual variable are u and v, therefore this one, so minimize z equal to what? Minimize z equal to u plus v, u plus 2v, and subject to the constant what? Subject to the constant 10u plus 2v, which is greater or equal to, I think, 11, then u minus 2v, which is greater or equal to, there is no second variable, that is y term, therefore greater or equal to 0, and the third variable is what? Third constant is minus u plus v, this is greater or equal to minus 1. Okay, so these three are the dual constant. Okay, so let's see that there are two variables only in the dual problem, therefore we can solve this problem by its dual. Okay, so by using the graph. Okay, so if we draw the graph, then first equation is this one, 10, this is the equation. Okay, 10u plus 2v. Okay, and this is the second equation, x minus 2y equal to 0. So this equation, and this is the third equation, because I using a software for this graph. Okay, you can also use the best software for your graphing calculator, which is GeoGebra. I always use GeoGebra for graph. Okay, so you can also use GeoGebra. This is, you can get the mobile app also, mobile app, and you can use the desktop version, that is the website. Okay, you don't need to download any software for the version, you just use using your Google Chrome or any other browser. Okay, so this is the graph of the given equation, given problem. Okay, now the equation, this is the equation 1, this is 10u plus 2v, this is equal to 11, and number 2 equation is this one, this is the second equation, which is u minus 2v, this is equal to 0, I think, yes, and the red one is minus u plus v, this is equal to minus 1. Okay, so this satisfies the first inequality is greater or equal to, satisfies, if we put 0 0, then the region is away from the origin. Okay, so the first one is this one, so this side is the given region, and for the second constant x minus 2y greater or equal to 0, if we take any point, if we take suppose 1, you can take 1 1, if we take 1 1, then if we put the value 1 1, then this gives what? Negative, and which is what? The second line is, I think, u minus 2b equal to 0. If we put, suppose 3 0, suppose if we put 2 0, then this gives, this does not satisfy. Okay, if we put 3 0, then 3 minus 2, which is greater or equal to, this satisfies the inequality, therefore this is the 3 0 3 0, this side 3 0, so this side is the given region. Okay, and the remaining point, the remaining is what? U minus u plus v. If we put 0 0, then 0 0 0 greater or equal to minus 1, which is correct, therefore the region is towards the origin, that is in this side. Okay, therefore the common region is what? The common region is this one. Okay, this is the common region. Okay, now we find, if we find the points, that is the extreme points, that is the three extreme points are this one, and this one. I just put the values. Okay, so this is the 0.21. You can see the value 2 and 1. Okay, and this is the value, I think x1 equal to 1 and 1 by 2, 1 and 1 by 2, and this is the value, I think 12 by 13, 13 by 12 and 1 by 12, I think. Okay, this, suppose these three are the points, because just a minute, I'll check once, just a minute. Yes, these three are the extreme point. Okay, you can calculate as your own, for your own. Okay, now if we calculate the value of the objective function of the dual of this problem, the objective function is u plus 2b. Okay, so this is u, sorry, z equal to u plus 2b, and we have to what? We have to minimize the functions. We have to minimize. So at 1/2 the value of z, this is equal to what? 1 plus 1, this is equal to 2. At what? At 2 1 the value of z, this is equal to what? This is equal to 2 plus 2 into 1, this is equal to 4. And at 13 by 12 and 1 by 12 the value of z equal to 13 by 12 plus 2 into 1 by 12, this is equal to, I think, 14 by 12. Okay, just a second. This is equal to 14 by 12, or 13 and 2 15. Okay, so 15 by 12. So see, this is the minimum most value, which is nearly equal to 1.2. okay, so the minimum value of z in the dual, in case of dual, is 1.2, which is the maximum value. Therefore the objective value of the objective function of the dual of this problem is equal to 1 by 2, which is equal to the value of the objective function of this maximization problem, which is equal to 1.2. Okay, so these are three questions from GATE 2016, 2015, 2016 and 2015. Okay, so this is the problems and this is the question. So this is the ends of this video, and if this video is helpful, then please give a like to this video, share with your friends and subscribe the channel. And one more thing is that I think all types of questions of the GATE LPP are covered. Okay, there are not any other types of problems in the GATE. We already solved GATE from GATE 2022 to 20, I think 15. Okay, you already solved this year of GATE papers, and we already solved various types of problem. I think there is no need for going the further years, for solving the further years, further back years, or previous year, you can say. So this ends these sessions. And I what one more thing is that I started from GATE lecture 1. Okay, LPP lecture, LPP lectures, lecture 1 to, I think there are total 15 or 16 lectures for LPP. Okay, and then we solve the previous years 2021 ka and 2022 ka kuch problems we are already solved for after the GATE exam. That is, these are the videos, are the older videos, and after that we solve the remaining problems of GATE 2022 and the remaining back years, that is from 2020, 2019, 2018, 2017, 2016 and 20 up to 2015. Okay, so the all questions of 2022 to 2015 are already solved in this you can say playlist, in this playlist section. Okay, so you can choose or you can check those videos for your help. Okay, for your GATE exam. Okay, so this ends these sessions. Okay, in the upcoming sessions, I think I'll discuss the numerical analysis. Okay, NA for the GATE with theories and the previous year problems. Okay, so keep watching the learning field. Thank you. And one more request is that we are very close to 1K subscriber. Okay, so please like, comment and share my channel to grow fast, to grow more, to complete 1K subscriber very fast. Okay, so thank you. See you again in the next video.